All right, so 9-6 is graphs of polar equations. So we're going to take the stuff we know about the points and we're actually going to put it into an equation and we're going to have to plot points and we're going to have to draw these really strange graphs. Okay, one is a circle, which is not that strange, but the rest of them are things you have not seen before. So we're on a polar coordinate grid just like the one we were before. This one has the over 12s, which fall in between. So like you'll see an over 12 here. In between all of the over 6s, over 3s, and then the X and Y axis. You'll see these over 12s now. It's just another spot for you to plot a point. So if I had given you like the coordinate point 2 and then 11 pi over 12, you would just know to go to 11 pi over 12, which is over here, and I'd go out to the second ring and I'd plot my point just like that. The difference between what we did before and what we're going to do today and tomorrow is that we are now going to plot these points, connect these points, and we're going to make some sort of a shape. So there's a lot of plotting points. There's a thing to test for symmetry, that kind of stuff, which is what we're going to start today. We won't get to all of it today, but we'll start it today. Oh, that's right. AP Chem is Friday. Thanks, Sai. I knew something big was this week. It's like A Push and AP Chem that are bad this week. The good news is 10.1 is like the world's easiest section because it's all stuff you already know. That's the good stuff. Okay, so if you have no idea what your graph looks like, just like in any other kind of graph, you can always fall back on plotting points. So we're going to graph this equation, plotting points, because we literally have no idea what r equals 4 sine theta looks like yet. So I'm going to take the chart that's below it, and I'm literally going to plug in those points. So I would do r equals 4 sine of 0. And then you want to think about your unit circle. If you don't have it, you can pull it in. I can look at 0, which is right here on my x-axis, and I can ask myself, what is the sign there? And the sign there is 0, because it's the y-coordinate. So I'd get 4 times 0, which is 0. So when when theta is 0, r is also 0.
Mommy, need to plug
Babe.
Need to plug my computer in.
Okay, plug it in. You can come over here.
Okay.
Yeah. Guys, for the black screens, don't forget that if you want to earn some extra points, you got to keep those screens on. Just a friendly reminder. Okay, then I'm going to plug in pi over 6. R equals 4 sine pi over 6. Pi over 6 is here. Sine is the y, which is 1/2. So r equals 4 times 1/2. And r equals 2. Continue plugging in points. Now I go to pi over 3. So r equals 4 sine pi over 3. Pi over 3 is here. The sign there is root 3 over 2. So this would be 2 root 3. Then I go to pi over 2. R equals 4 sine pi over 2. Pi over 2 is here. 4, the sign there is 1, so this is 4. And I'm just going to keep moving around. R equals 4 sine 2 pi over 3. And I get 2 root 3 again. And then I go to 4 sine 5 pi over 6. I'm here. And I get 2. I go 4 sine of pi. And that y is 0. I go 4 sine 7 pi over 6. 7 pi over 6 here. Negative 1/2. So I get negative 2. 3 pi over 2. Sign there's negative 1. Almost done. 11 pi over 6, which is here.
Can I have a banana?
Yes. Negative 2. And the last one, r equals 4 sine 2 pi. which is back to being 0. Here's the good news. We won't have to do all those points again because we're going to learn how to test for symmetry and that stuff. But let's just say you have no idea, right? Let's say you freak out, you forget symmetry, or you don't know what a graph looks like. This is something you could always fall back on, okay? So now I have all these coordinate points, and these are polar coordinate points. Who's still copying it down? I know I wrote that fast. Okay, so now I'm going to plot these coordinate points. 0, 0 means you don't move left or right at all, and you don't move up or down at all. You're literally at the pole. Pi over 6, 2 would mean I'm going on the pi over 6 line, which is here, and I'm going out to the second ring, which would be here. Then I get pi over 3, 2 root 3. So we know that this, we are going to approximate this when we graph it. The square root 3 is like a 1.7. Multiply that by 2, and I get 3.5. So this is 3.5. This is 3.5. So now I'm going pi over 3 and 3.5. Pi over 3 is here. 1, 2, 3.5 means my coordinate point's there. Then I go pi over 2 and 4. So on that vertical axis, 1, 2, 3, 4. Then I go 2 pi over 3 and 3.5. 2 pi over 3 is here. 1, 2, 3.5. Then 5 pi over 6 and 2, which is here. And back to pi 0, so I'm back at the pole. You with me so far? Yeah? Okay, then I'm going 7 pi over 6, negative 2. 7 pi over 6 is over here, but negative 2 moves me away from that angle, right on top of the dot I already have. Then I'm at 3 pi over 2, negative 4. 3 pi over 2 is down here, but negative 4 brings me back up to the coordinate point I already have. (11 pi over 6, negative 2). 11 pi over 6 is on the right in that fourth quadrant, but the negative 2 brings me back across. And then the last one I've got is 2 pi, and it's back at 0. So what's happening here is I'm getting this cyclic pattern, which should make sense, right? We know sine and cosines repeat like that, okay? So no matter how many points I would continue to plot, this circle-ish shape, we don't know exactly, it's perfect for now, but that shape is going to just keep repeating those points. So a circle is one of the types of graphs you can get for a polar equation. Let me see that. There was something I wrote down.
Parsley, butter, shrimp, and spinach. You need
Oh, that was
cheese
Costco
sticks.
stuff. Yeah.
I can do that tomorrow.
Okay.
Don't run the dishwashing machine.
All right. Questions on that graph? We're good? My child is doing PE right now. He's literally doing jumping. Sorry, it's very entertaining. Yes, Madeline. I know I can't let her in. You can tell her, but it's after attendance, so I can't let her in. Sorry. Thank you for letting me know. Okay, so now we're going to learn a couple of things that are going to help us to eliminate a lot of that work. The first is symmetry. So remember, the vocab terms are a little bit different now because we're dealing with a polar axis, but it says it's symmetry with respect to the pi over 2 line, right, which would be the same thing as your y-axis. So if something is symmetric to the pi over 2 line, then I can fold it left to right and it will overlap. So the circle that we just plotted, which is what that dark circle is, would be symmetric to the pi over 2 line. And I'm going to teach you a test, like a quick test and a long test, to find out if something is symmetric to the pole or to the pi over 2 line. So let's think about, well, what's the benefit of knowing it's symmetric? Well, if I knew it was symmetric and I ended up with this point and this point, I know I can just duplicate those points over to the left, and now I don't have to find anything on the left-hand side. Then there's symmetry in respect to the polar axis. Remember, polar is the same as the x-axis. If something is symmetric to the polar axis, then I can fold it along that pi line, or the polar axis, top to bottom, and my graph would overlap. This one does not have x-axis or polar axis symmetry because it doesn't overlap. And then the last one is symmetric in respect to the pole, which means you can like fold it down and over or diagonally. And again, this one does not have symmetry to the pole. But I'm going to teach you a test to figure out what does and what does not. So here's how it would look if it was coordinate points. If I had something that was symmetric in respect to the pi over 2 line, and then I found this coordinate point, the r theta, then I could know I could duplicate it over here to the left. If it was respect to the polar axis, and I had a coordinate point up here, then I could fold it top to bottom, and it would duplicate on the bottom. And then if it was symmetric with respect to the pole, if it's in the top right corner, so if it's in the first quadrant, I duplicate it in the bottom left, in that third quadrant. Or if it was in the top left, I duplicate it down to the fourth quadrant. So it's diagonal. Now here's the long way to test for symmetry. If you're testing for something to be symmetric to the pi over 2 line, then you can either take your variables, r and theta, and replace them with r pi minus theta or negative r negative theta. This is an or, so you could literally choose either one. For me, when you start to add and subtract, it gets confusing for people, so I would always choose the one that doesn't have it. So in my equation, that was r equals 4 sine theta. If I wanted to see if something was symmetric to the pi over 2 line, I would make this negative and I would make this negative. And then think about what happens with our even and odd functions. Hopefully you remember that sine, if it's negative theta, that's the same thing as negative sine theta. If it's tangent, same thing would be true, negative tan theta. And if it's cosine, the negative goes away. Those are your even and odd functions. So if I do what I just did with this equation and I make theta negative, it's the same thing as putting the negative at the front, and I get negative r equals negative 4 sine theta. If you remember symmetry, our test for symmetry with x and y axis, it either has to go back to the original equation or everything has to be the exact opposite, which is what would happen here. So the equation we just graphed would have been symmetric to the pi over 2 if we had done the algebraic test. If you're testing to see if it's symmetric to the polar axis, then we take that r theta and we replace it with just negative theta, so the r doesn't change. So if I use the same one we just did, it would be r equals 4 sine negative theta, and that would be r equals negative 4 sine theta. That did not go back to its original, and they're both not the opposite, so this one would have failed the test for the axis to the polar axis. For the symmetry to the polar axis. And if you look at our graph, it was not symmetric to the polar axis. And then the last one is the pole, and the pole, we change r theta to negative r theta. So if I use that same equation, it would have been negative r equals 4 sine theta. And the negative on the r changed just part of my equation, so it would have failed that test as well. So for pi over 2, we change both For the polar axis, we do theta to negative theta. And for the pole, we do r to negative r. Those are the tests, algebraic tests for symmetry. And then simplify it. So now here's the super fun part about polar, is that just because it fails, it doesn't mean it won't happen, which is, it seems ridiculous. I don't know why that's the case, but it's true. So just because it fails, it doesn't mean it won't happen. It could fail your algebraic test and still have symmetry, but what it is guaranteed a yes. So if you get that it is symmetric, it is 100% symmetric to whichever those tests are. But if you get that it's not necessarily going, when you go to graph it, it may actually have that symmetry. So I would never say you'll use it as a guaranteed no, but you can use it as a guaranteed yes. Does that make sense? Yeah. Folks in the classroom, you alive? Yes. Oh, Lord. Okay. Here's the quick test, okay? Because of our even and odd functions, because the sine of negative u would end up negative sine of u, and the cosine of negative u would end up as positive cosine u, the short tests are that if your equation has a sine in it, then it's symmetric to the pi over 2. And if your equation has a cosine in it, then it's symmetric to the polar axis. So if it says to test it algebraically, you want to do what we just did. But if you're just graphing it and you want to follow the quick test, you can totally do this. There's no quick test for the polar axis, for the pole, but there is this quick test for polar and for pi over 2. So think sine is, for me, how I remember it is sine is my y, and the pi over 2 is the y-axis, and the cosine is your x, and the polar axis is your x-axis. So that's how I remember the quick test. Okay, if it has sine in it, so if you go back to the equation that we started with, r equals 4 sine theta, we had sine, and sine is symmetric to the pi over 2 axis. All right, you with me so far? Yeah. Okay, so this one, again, we're given an equation. We don't know what it's going to look like yet, but it says to use symmetry to sketch the graph of it. So when I look at this equation, the quick test tells me it's going to have what kind of symmetry? Yep, polar axis. So polar axis symmetry. Thanks, Matt. Which means I'm going to pick to plot some points. I always do my quadrants. So I'm going to do 0. I'm going to do pi over 2. I'm going to do pi. But then I'm going to plot maybe a couple points in between. And then I'm going to duplicate it over the axis. So let's say I do pi over 6, pi over 3, 2 pi over 3, and 5 pi over 6. Then all of those points I got at the top, I'm going to flip and also do at the bottom because this is symmetric to the x-axis, which is the polar axis. So now we plug in, but we plug in less points. So I start with r equals 3 plus 2 cosine of theta, and I'm going to make theta 0. So I'm going to start here and work my way around. So at 0, cosine is 1. This would be 3 plus 2, which is 5. So my first coordinate point there would be theta is 0, the radius is 5. Oh, so switch that, sorry. 5, 0. Then I go r equals 3 plus 2 cosine. I'm going to go to pi over 6. The coordinate point at pi over 6 is root 3 over 2 and 1/2. So I get 3 plus 2 times root 3 over 2. 3 plus these cancel. Root 3 would be my exact point. We're going to approximate root 3 to be 1.7. So this would be 3 plus 1.7, which is 4.7. So r is 4.7. Theta was pi over 6. Then I plug in pi over 3. r equals 3 plus 2 cosine pi over 3. That coordinate point would be 1/2 and root 3 over 2. Cosine there is 1/2. 3 plus 1 is 4. So 4 n pi over 3. You with me so far? Yeah. Okay, now I'm going to go to pi over 2. My coordinate point here is 0, 1. So I go r equals 3 plus 2 cosine pi over 2. 3 plus 2 times 0. 3 plus 0, which is 3. And it's 3 pi over 2. Then I go pi over 3, 2 pi over 3, sorry, which is negative 1/2 and root 3 over 2. So I get r equals 3 plus 2 cosine at 2 pi over 3. I get 3 minus 1, which is 2. Five pi over 6. Coordinate point there is negative root 3 over 2, 1/2. So 3 minus root 3, which we said we're going to approximate to be 1.7. So this is 1.3. And then the last one is pi. Coordinate point there is negative 1, 0. Everybody still with me? All right, so now I have to plot all those points. So I'm going to start with 5, 0. At 0, I'm going out to 5. So at my 0, theta, I'm going all the way out to 5. 1, 2, 3, 4, 5, which is that blue ring. At pi over 6, I'm going to 4.7. So at pi over 6, 1, 2, 3, 4.7, close to the 5, but not quite there. At pi over 3, I'm going to 4. At pi over 2, I'm going to 3. At 2 pi over 3, I'm going to 2. At 5 pi over 6, I'm doing 1.3. And at pi, I'm doing 1. You with me so far? Okay, so now every point that's above the x-axis, because this is symmetric to the polar axis, has a duplicate point on the other side. So I'm going to plot those points. So at the pi over 6, this pi over 6 should match the one that's at 5 pi over 6, which was like a 1.3. At 2 pi over 3, I'm going to come down here and match it down here. It was 2. At pi over 2, I'm going to come down here, and it was at 3. At pi over 3, I'm going to come down here, match it at 5 pi over 3. It was at 4. At pi over 6, it was at 4.7. So I'm going to match it down here at the 11 pi over 6. So everything that was above the axis now gets duplicated underneath the axis. Because again, we have polar axis symmetry. And now I'm going to connect these points. So this is one of these weird shapes, which we're going to learn in a minute. It has something like this. It's like a kidney bean, sort of, okay? So we're going to learn this has a name, and we're going to learn some classifications of it. But for right now, if you knew nothing else, that is, we know it has the polar axis symmetry, which means we're going to duplicate the points above and below. And then we would just connect them as best as you can. Questions on that one? So if this was a sine graph, we would take anything that's to the left of our pi over 2 line and we would duplicate it over the pi over 2. Because it was cosine, we duplicated it over the polar axis or the x-axis. All right, so these shapes are called limisons. Within a limison, there's 4 classifications, okay? So a limison is like the parent name, and then within the limison is one with an inner loop, one that's called a cardioid or cardioid, which is a heart-shaped, one that's called a dimpled limison, which is kind of like that kidney bean shape, and then a convex one, which literally has a flat edge. So it's like a circle with a flattened edge. So again, Corona perk, you can have something like this that helps you on your test. Previously, they would have had to know what, based on, and I'm going to teach you the relationship, but based on the relationship between the A and the B, what is that shape supposed to look like? So a limison happens if I have a number plus or minus a number sine of theta, or a number plus or minus a number cosine of theta. So if I have something that is being added or subtracted to a sine or cosine, now mind you that this can be 1 and this can be 1. So it could be like 2 plus or minus sine of theta. It could be 4 plus or minus cosine of theta. Okay, it could be 1 plus or minus 3 sine theta, something like that. But there is something being added or subtracted to my trig function. If that's the case, then I get what's called a limison. The A is the number that's by itself. The B is the number that's attached to the trig function. If A over B is less than 1, then it has an inner loop. So it comes in around the axis like that. Now these can also be on the y-axis, so these can also be rotated. If it's A over B equals 1, it has that heart shape. So think it's found the perfect match, okay? So it has its heart shape. If it's in between 1 and 2, then it's called a dimpled limison, which is kind of like that kidney bean shape. And if A over B is greater than or equal to 2, then it's convex, which means it's just flat on the one side. Okay, if we go back to that example. First of all, it's plus or minus, so I know this has to be a limison. But now I want to look at A and B. So A over B, which would be 3 over 2, where does it fit in this range? A over B is not less than 1. A over B is not equal to 1. A over B is 1.5, which means it falls in between 1 and 2. So it's called a dimpled limison. So if you look at our graph, if I had known that ahead of time, I would have known to make this curve a little bit softer. So it shouldn't be so pointed, okay? So that's one of the tools you're going to use is it a limison? If it is a limison, which one of these is it? Does it have the inner loop? Is it heart-shaped? Is it dimpled, or is it convex? And then based upon that, you'll know how to make that little scoop. Is it supposed to be sharp like a heart? Is it supposed to be flattened like a convex? Or is it supposed to be like smooth like the one we just did? Or should you have duplicate points? And you'll see when you have like an inner loop, you'll result in like duplicate points that they go in and out, and you'll get that loop shape. But again, that's the first classification. Sorry, go ahead, Matt. Limisons. Oh, right. So they could have, let's say it was a sine. Let's say this equation we just got was sine. R equals 3 plus 2 sine of theta. Then it's actually going to be on the y or the pi over 2 axis. So it does like this kind of shape, like that. Yeah, so it it depends on which way it's facing. And if it was a minus, it could be upside down, right? If it was a minus cosine, the dimple would be on the right-hand side instead of the left. So that you'll get from your coordinate points. Like, you're gonna have to plug in coordinate points. So when you're gonna see there's a bunch of different types of these graphs. If you're gonna classify it first. Is it a limison? You're gonna see we're gonna get to a couple other kinds. If it's a limison, which of the 4 kinds of limison is it? So you're gonna get more specific. You're gonna look for symmetry, and then you're gonna plot your points, and then you're gonna draw it at the end. Everybody good so far? Okay, so next up is a rose. These are the prettiest, and honestly, I think they're one of the easiest ones. Okay, this is called a rose because they call those things petals. So they have those little scoops on them, okay, which are called petals. If it's a rose, then you determine how many petals it has. So it's not like where you have a limison and you have 4 different kinds. Once you figure out that it's a rose, you just have to figure out how many petals it has. And the petals is determined by the number next to the theta. So notice that these equations, none of them you're adding or subtracting, because that would have been a limison. The difference in a rose and how you identify as a rose is that there's always something being multiplied by the theta. So this could be r equals cosine 2 theta. This could be r equals 5 sine 4 theta, okay? This is fun. Okay, so if that's the case, then you look at the number next to the theta to determine the number of petals. If the number is even, well, let's start with what it says. If the number is odd, then you don't change that number. That is the number of petals. So if my equation had said r equals cosine 3 theta, then there are 3 petals. Odd stays the same. If that number is even, then you double it. So in 2 theta here, this would have 4 petals. And 4 theta, this would have 8 petals. So again, if there's a number next to the theta, we know it's a rose. If that number is even, we double it to get the number of petals. If a number is odd, we keep it the same. And that's how many petals it is. So now you've got 2 things to look at with a rose. Is it symmetric? Because if it's symmetric to the x-axis, you should be able to fold it top to bottom, like this one, like this one. I can fold those top to bottom and they would overlap. And how many petals there are. If it's symmetric to the pi over 2 line, because it has sine in it, like these 2, I can fold it left to right. Now, a lot of rose graphs are also symmetric to the pole, okay? But again, the easy checks are the pi over 2 and the polar axis. Then the second thing you want to look at from a rose is the number on the front of it. Whatever number is here, so whatever the A is, that's how long the farthest point on your petal is. So if I pick this one, then my A is what? If I have r equals 5 sine 4 theta, what's my A? So the 4 is going to determine the number of petals. That's the N. The A is on the front, right? So what's A? 5. So that means the furthest the petal goes is 5. That means from like, this doesn't have, it would have 8 petals. 1, 2, 3, 4. So let's say it's this one. This A would be 5. Whether it's there or there or there or there or there or there, whatever it is, the furthest point out on that petal is going to have a radius of 5. So you're going to, if it's a rose, number of petals, the length of the petal, and symmetry. After you get those, well, I'm not doing this today. After you get those, then you'll graph it by plotting your points. All right, I'm gonna skip to here. Okay, I'm gonna skip to example 3, and then we'll finish with the lemniscates and the circles tomorrow. But I want to do a rows with you. So example 3 says analyze the graph of 4r equals 2 cosine 2 theta. Identify the type of curve, the symmetry, the zeros, and then verify the graph using a graphing calculator. So by looking at this, we know it's what kind of shape? It's a rose. And you know that because 1, I told you I'm going to graph a rose, but 2, because the number in between the trig function and the theta. If a number is there, then it's a rose. How many petals does this rose have? It's got 4 petals, and we know that because it's an even number, so we double it. What's the length of the petals? 2, and we know that because of the number on the front. Does this rose have symmetry? Yes, to what? What trig function's in it? Cosine. Cosine is the x, right? Good. We call the x-axis the polar axis. So this is symmetric to the polar axis. Which means whichever way my rose is going to go, it could either be like this, and then it would duplicate down here, because that would be symmetric to the x-axis or the polar axis. Or it could go 1, 2, 3, 4. That would also be symmetric to the polar axis. The way I know which way it's going is by plugging in points and finding where that 2 happens. So if it's here, think about it, the 2 is actually going to be halfway between, which should happen at pi over 4. And if it's this one, it's going to happen at 0. So you'll find those by plugging in your points, okay? But think about how it's going to happen. It's either going to be, like the top and the bottom, where if I plug in pi over 4 here, 2 cosine 2 times pi over 4 would be 2 cosine pi over 2. At pi over 2, my coordinate point is 0, 1. The cosine there is 0. So my coordinate point there is going to be 0. That means my graph does not look like this. It probably looks like this. 2 cosine 2 times 0 would be 2 cosine at 0. The cosine at 0 is 1. 2 times 1 is 2. Now I found my petal. So I know it goes here. If it goes there, it has to come over here because the roses in general are symmetric. And then whatever happens on the bottom is going to happen on the top. So I would plug in at pi over 2. I would plug in at pi. I would plug in at 3 pi over 2. And I should have a 2 at each of those points. And then I have found all 4 petals. On the graphing utility, because I'm going to show you that real fast, you have to be in polar and radians. Hang on, let me swipe. Okay, so I'm in polar and radians. And remember, if you're in polar and radians, then my variable is going to be theta. So I go to the y equals, I would do 2 cosine 2 theta, hit enter, hit graph. And there's my rows. If I zoom in on this, I'll find that those points are directly at 2. Like on the right, it goes out to 2. On the top, it goes up, left, and down. You will not graph these using, you can graph them to check your answers, obviously, which is why I'm showing you. using a graphing utility, but on your test, you'll have to give me the symmetry, you'll have to give me the number of petals, that kind of thing. It'll depend on what kind of question you get as to what information you're gonna have to give. So just keep that in mind. So tonight's homework, I did it on WebAssign. It does have multiple choice, okay? But I want you to keep in mind that you need to do the graph first before you pick it on multiple choice. Homework's not due till Wednesday because we didn't finish it, but feel free to start graphing the roses and the ones that you're adding and subtracting a number, the Limisons, and see if you can do them on your own. And then tomorrow I'll finish and we'll go over any kind of questions you've got. Bye, guys. Have a great day. Here.